Hello everyone, today we're going to be working on fundamental problem 7.4 and this problem is asking us to determine the normal force, shear force, and moment at point C. So our first step is going to be to doing the cut right at point C. From there, what we're going to do is we're going to analyze both sides of the beam to see which side would be easier to work with. If we were to take a look at the left side of the beam, we could see that we have a pin support at point A, meaning we're going to have two unknown reactions, our vertical reaction and our horizontal reaction. So we would have to solve for two unknown reactions. Meanwhile, on the right side, we have a roller support at point B, meaning we're only going to have one unknown reaction, which is our vertical reaction. And because of that, I'm going to be working with the right side of the beam since it would be easier. Now that I've decided which side of the beam I'm going to be working with, the next thing that I'm going to do is I'm going to solve for the value of the reaction. But before solving for it, what I'm going to do is I'm going to find the concentrated force of this distributed loading that we have on the beam to then be able to find the reaction of to then be able to find the value of our reaction. So I'm going to be calling this concentrated force F1. And to find the concentrated force, we just have to take the force and multiply it by the span that it is on the beam. So we have 9 kilonewtons over meters times, and we know that there is this loading of 9 kilonewtons over meters for a span of 3 meters. So multiply that by 3 meters. From there, our meters would cancel out, and we would end up getting a value of 27 kilonewtons. So we know that our concentrated force of that loading is of 27 kilonewtons. Now, as for the location of that concentrated force, since this is a uniform loading, we know that since it's a uniform loading, it's going to be found right in the middle of that loading. So as you guys could see, once again, the loading goes on for 3 meters. So half of 3 meters is 1.5 meters. So we could say that it is right here, about on top of point C. So now that we found our concentrated force, the next thing that we're going to do is we're going to be solving for our reaction. Since it's a vertical reaction, we have to assume if it's going to go upwards or downwards. I'm going to be assuming that it will be going upwards, and I'm going to call it B sub y. So to solve for my reaction and not having to solve for the other reactions, what I'm going to do is I'm going to be taking the sum of the moments about point A. That way the reactions at point A will not be creating a moment. And I would simply just be solving for our reaction B sub y. So if I were to take the sum of the moments about point A, we know that all of that has to equal 0. So we have our 14 kilonewtons acting downwards to the right of our point A. So we know it's going to be creating a clockwise moment, meaning a negative moment. Moment is equal to the force, so 14 kilonewtons times the distance, and we know that from our point A to our 14 kilonewtons, there is a distance of 1.5 meters. From there, we have our concentrated force. It is also to the right of our point and acting downwards. So once again, it's going to be creating a clockwise moment, meaning a negative moment with a force of 27 kilonewtons. And then the distance, we know that from here to here, there is a total distance of 4.5 meters. And then from there, we have our reaction B sub y. It is to the right of our point. but this one is acting upwards, so it will be creating a counterclockwise moment, meaning a positive moment. The force, that's what we're trying to determine, and then the distance from here to here, we know there is a distance of 6 meters. So we have a positive moment. We don't know the force, that's what we're trying to determine, and then the distance, 6 meters, and we know that all of that has to equal 0. So from here, we would simply just be solving for a reaction b sub y. So we would get, let's simplify this down a bit, we would get 6b sub y is equal to 142.5 kilonewton meters. From here, we would solve for our reaction b sub y, giving us a value of 23.8 kilonewtons. And since we ended up getting a positive number, that means that we assumed correctly, meaning that this reaction will be going upwards. Now that we have our reaction b sub y, the next thing that we're going to do is we're going to be drawing a free body diagram of the side of the beam that we're going to be working with. So in this problem, we're dealing with the right side of the beam, so I'm going to be drawing a free body diagram of the right side of the beam. So as you guys can see, our free body diagram will consist of the 1.5 meter span of the beam with the distributed loading throughout the whole beam that we're working with, our reaction at b sub y, and our cut will be on the left side of the beam. So we could go ahead and draw that out. So we said our beam, and all that beam will have the distributed loading on it. From there, we have our reaction right here. Our reaction b sub y, we said that it has a value of 23.8 kilonewtons. From there, we said this distributed loading, we know that it has a weight of 9 kilonewtons over meters. We said that we have our cut on the left side, and then from there, we know that the beam has a span of 1.5 meters. So now we're gonna include our shear force, our normal force, and our moment based on the sign convention. So since our cut is to the left side, we know that our shear force will be going upwards. And we're gonna name that E, that's our shear force. Our normal force will be going away from the cut. So we're gonna call that P, or you could also write that as N. And then from there we have our moment, and our moment will be going clockwise. So now, before determining the value of our shear force and our normal force, our next step would be now determining the concentrated force for this 1.5 meter span of the beam. So we're going to do the same thing. I'm going to call this one F2. And we're going to solve the concentrated force the same way. So our weight of 9 kilonewtons per meter, and then multiply that by 1.5 meters. And we know that that will give us a concentrated force of 13.5 kilonewtons. And once again, since this is a uniform loading, we know that it's going to be halfway. So half of 1.5 meters is 0.75 meters. So we said 13.5 kilonewtons. And we know that it is half. So we know 0.75 and 0.75. So now that we know all of this, now we can proceed to finding the values of our shear force, normal force, and moment. So the first thing that I'm going to do is I'm going to be taking the sum of the forces in the x direction to solve for our normal force. And as you guys could see in our free body diagram, our normal force is the only force in the x direction. So that means that our normal force will have a value of 0. So remember, this is our normal force. From there, to solve for a shear force, I'm going to be taking the sum of the forces in the y direction. Once again, those have to equal 0. So based on the sign convention, we know that our shear force will be acting upward, so that's a positive force. So we have V. From there, we have our concentrated force of 13.5 kilonewtons, so that's a negative force. And then from there, we have our reaction, B sub y, with going upwards, so that's a positive force of 23.8 kilonewtons. And we know that all of that will have to equal 0. From here, we would simply just be solving for our shear force, or our V. And we end up getting that our shear force has a value of negative 10.3 kilonewtons. So remember, this is our shear force. So now to solve for our moments, what we're going to be doing is taking the sum of the moments about the cut, or about point C. We know that that will have to equal 0. So here we have our moments going clockwise. So that means that's going to be a negative moment. From there, we have our concentrated force on the right of our cut going downwards. So once again, creating that clockwise moment. So another negative moment with a force of 13.5 kilonewtons and a distance of 0.75 meters. And then from there, the other force that is going to be creating a moment is our reaction. We have our reaction going upwards to the right of our cut, so this will be creating a counterclockwise moment, meaning a positive moment with a force of 23.8 kilonewtons and a distance of 1.5 meters. And all of this has to equal 0. So from here, we would simply just be solving for our moments. So we would end up getting that our moment has a value of 25.5 kilonewton meters. So remember, our M is our moment. And with that, we are done with this fundamental problem 7.4. So once again, this problem was asking us to solve for to determine the normal force, shear force, and moment at point C, which is why we decided to do the cut on the beam at point C. From there, we analyzed both sides of the beam and determined which side of the beam would be easier to work with. We decided the right side, since on the right side we just had one unknown reaction. From there, we found the concentrated force of that distributed loading that we have, and then we proceeded to finding the value of our reaction. From there, we drew a free body diagram of the side of the beam that we decided to work with. We added our shear force, normal force, and moment based on sign convention. And then from there, we took the sum of the forces in the x direction to determine our normal force, the sum of our forces in the y direction to determine our shear force, and then we took the sum of the moments about the cut or about point C to determine our moment. Thank you guys so much for watching this video. Please feel free to give this video a thumbs up if you found this video useful, and also feel free to subscribe to our channel if you guys would like to see more videos like this.